question. For delta H, positive and negative values? Yeah, we should see that. Should we ever see an activation energy be negative? No, it's always going up. So your activation energy will always be a positive value. Okay? So if I'm looking at this in my expression, I've got EA, I've got R, I've got T. The only thing I'm missing is A. Well, what is A? What must A be? Yeah, A is going to be that frequency factor. That's going to be our 1.5 times 10 to the 11th per second. Right? So when we talked through it, I said it was this constant that incorporated a whole bunch of things. It is still a constant that incorporates a bunch of things. It happens to be called the frequency factor. So knowing what the specific name is can be helpful. Is this your pencil? Who just lost a nice pencil? Everybody sign in? Trust that. Okay. There's more empty seats here, so we'll leave it here. Right? So now it's just a question of plugging in all the numbers and solving, except what do we do before we plug in all the numbers? We do have to watch out for our units. Okay, R is in units of joules. Activation energy is in units of kilojoules. So you are going to have to make sure that you deal with that unit conversion before you run your just bulk smashing numbers into the calculator. Does that make sense? Did anybody actually solve it all the way out? Just checking. I don't know what the number is off the top of my head, so I can't do that calculation in my head. All right, but you should be getting a value. What did you get?
16.6. Or 16.58.
And sig figs are going to be a mess with an exponential, so we'll just accept 16.6. What units do you think we should get for it? All right, there's all those units. Like, what should your final answer be for your units?
Whatever, inverse seconds.
It's just going to be inverse seconds.
There's all the units of the exponent.
Everything in the exponent cancels. Okay, so you don't have to worry about the units coming out of that. So the exponents for our final K will just be whatever A was, and A was inverse seconds. Okay. Why are you making a face at me? Did you not get 16? I'm trusting somebody else to get 16.
I'm just confused because I can't. I think I just need it worked out for me to be able to understand it. I don't know.
I mean, I can show you plugging in all the numbers. It's not going to make me happy. But if it makes you happy, 1.5 times 10 to the 11th seconds minus 1.
Is that a constant like throughout all equations or just the specific one?
When is that A constant? That A is constant for this particular reaction, whatever reaction you're studying here. This is going to be negative. Well, come on, pen, work with me. Negative. We're doing kilojoules, and I make it joules. It should be 56800. Did I do that right? Joules now per mole times 1 over my R, which was 8.314 joules. Because I have that in the denominator, I can drop my moles and Kelvin up on the numerator. And then my temperature 1 over, I already forgot the number. Oh, it was 298. 298 Kelvin. So what happens, our Kelvins will cancel, our joules will cancel. Run into this weird issue with this mole. I think in this case you're assuming one reaction cycle, so that mole will drop out too. So it's not actually joules per mole Kelvin, it's just joules per Kelvin in this particular cycle.
The mole cancels with the other mole.
Oh, there's another mole right there. Sorry, my bad. Okay, so our moles cancel out. And now it's punching it into the card. Is that good enough? Okay. I will say I didn't want to draw it out because it's really messy with all those exponents. I would make it really, 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 really big whenever I was trying to write out that calculation to ensure that I don't make mistakes with minus signs and placement of those things when I run through the calculator.
16.6.
Yeah. We've got at least one person telling me 16 point, I think you said 5.8, 5.8, and then a bunch of other numbers. What happened to the negative? It's right there.
Yeah, it's in there. It's in an exponent.
Yeah, it's in that exponent. Other questions about just calculator crunching this? Okay. After that, what we'd really want to move into is now what can we do with this or manipulate within it? So we could go through and determine the Arrhenius or the activation energy for an equation. So in this particular case, we went through and solved for the rate constant because that's how the equation was formatted, was to give us the rate constant. Right? That was the K equals A E negative EART, right? That's not typically how you would use it, right? Because the activation energy is not something we would easily know. Right? The activation energy is the distance between your reactant energy and your activation and your transition state. And since the transition state isn't a physical point, it's really hard to measure that value. Right? So instead, what we're using the Arrhenius expression for is actually to solve for the activation energy. Because we can get the rate constant by running a whole bunch of reactions, right? Determine what the rate law is, back calculate what the rate constant is. Right? If we look at our expression, the rate constant is something we can get experimentally. Temperature is something we can monitor. Okay? All we'd have as unknowns would be the activation energy and our A. Well, how do I know the A? Okay, you're right. In this expression, that's going to be really hard to figure out. Right? And so what we would end up doing, at least right now, typically what happens is you just take this data and you punch it into a computer, and the computer goes through and you tell it fit a logarithmic formula. So it fits to the logarithmic formula, and in that fit, it's going to spit out A and EA. Okay? You could theoretically do the same thing by just start changing the numbers A and EA to see what your plot looks like. Does it match the curve? And what you would find is that's going to be really painful to go through and do that fitting process. So what we would like is another way to format the data so that I can interpret it relatively quickly. Okay? So how can I manipulate this equation to get into a system that's a little bit easier to digest? Fitting exponential functions is not easy for the human brain to wrap. What is easy for the human brain to wrap around? Linear functions. Linear functions are lovely. A linear function would have what format? There it was. Y equals mx plus b. Okay? So we would change x, our variable, and we would see what the output was for y. We could collect enough of those pieces of data, plot the line. When we looked at that straight line, its y-intercept is b. Do that right? Is it? It's y. Y-intercept is b, and m is the slope. So I can pull a lot of information off that linear function really, really easily. And I could plot it and be like, yeah, a whole bunch of data points all fall in roughly a straight line. That makes a lot of sense. Okay? But this isn't in a format of y equals mx plus b. There's that nasty exponent. So what should we do?
Natural log.
Let's get rid of the exponent. And how do you undo an exponent? Natural log. So if I take the natural log of both sides, I get the natural log begins with an L for the record, not H. Natural log of our rate constant equals the natural log of this godforsaken thing. But now we would have to understand the mathematics on how we separate that out. How do we separate that out? Well, we can say the ln of A plus the ln of e to whatever. But the ln of e, cancels. It's just whatever's in the thing, which means my expression becomes the ln of A plus, it's going to get a little bit weird here, minus E over RT. Said another way, what we boil down to is the natural log of K will equal negative, that's an EA over R times 1 over T plus the ln of A. Well, that brings in a whole bunch of other stuff that I didn't want to worry about. Okay, well, but breathe. What is 1 over T? X. So now what I can do is instead of running a plot of temperature and rate constant, I can run a plot of 1 over temperature. That now becomes my X value. What do I plot with my rate constant? The natural log of K. Now when I run that plot, the slope of that line is going to be the negative activation energy over R. The y-intercept, the natural log of A. So I can pull that information off of a graph that now interprets what all those other missing pieces are. Okay? Who do we have to thank for being able to come up with things like that? Probably mathematicians. You can thank them. Okay? And it's pretty powerful, but that's what the vast majority of our plotting and finding of data usually comes down to, is how do we convert our formulas, our equations, into ways that we can plot them as straight lines. Because once they're plotted as straight lines, it's much easier for our brains to fit that data. We can get slopes, we can get y-intercepts, and we pull all of that geometry or trig, or that's probably one of those two classes, out, and we can set up a system that's easier to manipulate. Okay? If you want all that work, that's at 12 minutes, 12:13. So what do? We shift the linear form. And here's the linear form of that equation. And we go through and plot. What are we plotting? Our x, we're plotting 1 over temperature. Our y, what are we plotting? The natural log of K. So we will have to run a calculation on our data set before we plot. But once we now plot, we should be able to see a nice, smooth, linear relationship between all those data points. And that's pretty cool. Whereas if we had looked at the previous plot, and I'm going to crudely draw it, what do we have? Temperature versus K. You might get data points that look something like this. And you'd be like, well, is that a straight line with a little bit of variability in it? Or was that an exponential function? That plot becomes hard to nail down. So if you can rearrange your format so that you know you're absolutely in a linear relationship, that can smooth your transition and your interpretability of those individual systems. Kind of makes sense? All right, so once we have this plot, what information can we pull out of it? So for this particular activation, or sorry, not activation energy, for this particular reaction, what can we determine? We can determine the ln of K and 1 over T given the plot. I would argue the plot is what you used, and to get the plot, you had to know ln of K and 1 over T. So I would argue those two things, I could care less about. I already knew what the rate constant was. I could extrapolate what the rate constant would be for a different temperature, so I could pull that out.
The exact opposite of what I said. Yay.
There it is. So what I could do is now look at this plot, and I can recognize that I'm in the system y equals mx plus b. That's an x. The slope of the line, straight off my plot, was negative 37758, and that is equal to negative activation energy over R. Do I know what R is? Yeah, that was a constant. That's that 8.3145 joules per mole Kelvin. So what can I do? I can now solve for my activation energy. And my activation, but it's a negative. We said the activation energy can't be a negative. There's two negatives. Two negatives make positive. So 37758 divided by 8.3145. What are the units on that slope? The 37758 isn't giving us units. Where are the units coming from? 8.3145, which was joules per mole Kelvin. Oh my goodness. Algebra, right? The people that are laughing might recognize the algebra. Right? I didn't even recognize the algebra until I wrote down the unit. Because the unit for activation energy should be joules in the numerator. Is it in the numerator? No, because I apparently failed algebra. 37758 times R. That's what happens when you pass it through the equality. Okay? So our slope of that line is what's setting us up for our joules per mole. What's happening with the temperature? That's going to get canceled out dealing with the exponent. Or not our exponent, our x value. So we just take 37758 times 8.3145, and we now have our joules per mole for this reaction. That's going to be a wicked huge number, right? Do we want to report it as a wicked huge number? No, so what do? Convert it to kilojoules. 1,000 joules is 1 kilojoule. So I can divide it by 1,000, and I now get a cleaner number. And I have my activation energy. So cool. That's awesome given this plot. I now just pull that data straight off and I know my activation energy. Sweet. What else could I do? Because I know the y-intercept, I know B is equal to 24.641, and I know that is equal to the natural log of A. That's the beauty of matching to the equation of the straight line. How do I get rid of the natural log? Do the e to both sides, and I get e to the 24.641 equals A. If I want an actual numerical value, I enter it into the calculator. Kind of, sort of? Okay. So this is effectively just dealing with plug and chug on how we can manipulate it. So what is the activation energy for the reaction? What is the frequency factor? That's the work that we just set up. Right? And it's now just a question of plugging those numbers into our calculator and spitting out an answer. Make sense? Okay.
So,
Yes. Where?
for the M bracket, I'm kind of confused on what exactly. So you're saying that in this specific scenario that the negative 37,000 is equal to all of negative EA over R times 1 over T, or is it just the negative EA?
Negative 3,778 times X. What was X?
1 over T.
1 over T as a unit. That's it. We don't need a numerical value associated with it. Okay, as a unit. That is equal to, in my thing, times 1 over T.
So you're ultimately just looking for the negative activation energy over the gas constant. You can plug in your gas constant, multiply, and
That's it, yeah. That's pretty neat, right?
when
You just-
I've always been so confused confused by like the methods, like chemistry, like heavily uses, where you plug in where you lay out all of your units. And I feel like it just makes it way too confusing for me personally. I understand that's where it stands.
Yeah. So where I would push with that is as long as you're right with your units,
That's what
oh
matters.
well. It's less a unit and more there to cancel our temperature term from that system so we get our activation energy in the proper unit system. So kind of a shift. Reactions tend to slow down over time, which we kind of addressed really early on, which is why when we go through and ran our experimental evidence for individual reactions, what rate did we look at? When I defined the rate for a chemical reaction, what rate was it? Was it the rate after 5 minutes? Was it the rate after an hour? What rate did I use? I used the initial rate, by definition. That's what I go through and picked. Okay? That's the easiest 0-point comparison system for all those things. So I start with my initial rate. For whatever concentrations I'm dealing with, when I mix those things, the initial rate is what I use to plug in everything. But if I went through and looked at a reaction, as the reaction progresses, what happens to the concentration of my reactant? Okay, so in this case, we're saying we've got the reaction A goes to B. What happens to the concentration of reactant over time? It goes down. What is that going to mean to the speed of the chemical reaction? It's also going to slow down. There's fewer particle collisions. Okay? So this is going to be true for pretty much everything. We're going to see a slower rate. Okay? But what happens if we now change... Oh, sorry. Went the wrong direction. What would it look like, instead of looking at the reactants, I looked at the products? What's going to happen to the concentration of products with respect to time? Yeah, it should mirror the reactants. Okay? With a little bit of variability depending on the rate law in those expressions. Okay? But it should mirror that system. Okay? As time progresses, what happens to the concentration of product? The product concentration goes up. Eventually, what's going to happen? There's not enough reactants turning over to make products, so the product concentration starts to disappear. And the slope of any one point on this line is now the rate for that reaction. Okay, at that data point. Is there a different question that I saw? Oh, this is the question I saw. So if we go back to looking at our reactant, draw a graph that shows the reaction at a higher temperature. So what would our plot look like if I increase the temperature? And you could actually draw it, or you could just talk to the people at your table and try and figure it out. What do you think it would be?
Concentration goes down quicker. When there's less concentration.
So we consider the slope of the line as the change in A over the change in T. That's ultimately the rate for our individual chemical reaction at any given point. If we increase the temperature, what should happen to the rate?
Increase?
It should increase. Okay? So if the rate increases, that slope also needs to increase, which then means we're going to get a steeper line coming out of that. It's still going to kind of flatten off and plateau, okay? But that's ultimately what's happening when we increase our temperature.
Because the product is being used up faster, because the higher temperature, higher overall activation.
Why is the reactant being used up faster? Does the activation energy change? Nah. So why is the reactant getting used up faster when we increase the heat?
No, exceed that activation energy. I don't remember like the more specific term for it.
So if we look at heating up my pen and a cap, I can give them lots of energy. Does that mean I get a chemical reaction?
No.
So why, when heating it up, do we get faster chemical reactions? Increased collisions. Okay, we increase the probability of making those collisions. Okay, so it goes back to collision theory. The hotter the reaction, the more they're moving, and I was intentionally keeping my hands separated for that example. Okay, the more they're moving, the more likely they impact. And they impact with enough energy to clear the activation energy.
Right.
Okay, but we have to have that collision. So the more motion of our particles, the more likely we get an impact, the more likely we get a successful impact, and we can get potential products coming out of that. Okay? So, what we want to do is take a look at this simulation. It is a little blue box. If you've got a device in front of you, please navigate to that system, because I assume this is what she would actually do in class. I'm not positive about that, but that's how we're going to work it. All right? So I want you to go to this simulation. If you don't have a device to go to that simulation, that's okay. What I'll do is pull it up on my computer, and I'll play around with the dials and digits and see what happens. Does that make sense? I paused. Hopefully we paused. We don't want to. And that. Okay. Can I pause? Stop. Let's see what happens. Okay, let's see. Can I move the red bar? Nope, can't move that. Let's increase the concentration. What should happen to our speed? Our rate should increase. Okay, I have to reset it. Wow, that's annoying. Do you remember where the line was? Okay, so this should have dropped just a slightly steeper slope.
I think when you click reset, it resets all the numbers.
Oh, you. It did. Okay, that looks a little better. Now I feel like it's a steeper slope. Before I was like, I don't know about that. Okay, so we're seeing a steeper slope with initial particles. Okay, let's drop that back to our 250-ish. Reset. What happens if we change the volume? What do you guys think? Why should changing the volume change the rate? Because when we talked through all of the chemical reactions, did we talk at all about volume?
No.
Yeah, we did. We absolutely did talk about the volume. If I wrote a rate law, what's my rate law? Rate law equals, I wrote a K, good. K is, then now what?
Concentration.
Concentration of our reactant. Let's just stop right there at concentration. What are the units of concentration?
Moles per liter.
Moles per what?
Liter.
What is liter a measure of?
Volume.
Did we change the volume?
Yes.
Sneaky. Okay? So if we increase the volume, what's that going to do to my concentration? Okay? Did I say increase or decrease? What did I say? Let's increase the volume. What should happen to my concentration? It should decrease, which means what happens to my rate? Should also decrease. Okay? So volume does contribute to these things. Okay? And if I relate volume and moles together, I can convert or relate my moles and my volume to P word,
Pressure.
pressure. So when we talk about our rates, we'll typically look at concentrations and we'll also look at pressures. Okay? Both of those are valid unit systems to go through and use. If we decrease the volume, what's going to happen to my rate? I got to reset it. Wow, it does weird things. Okay, and we should see that faster rate again. Make sense? Reset. What happens with our temperature? We've increased everything, so let's decrease. Let's decrease the temperature. See all your particles? They're moving slower. And by moving slower, what happened? True, your rate decreases. What's happening in the blue box?
They're not hitting as often.
They're not impacting as often. And because we're reducing the amount of impacts, we reduce the speed at which our chemical reaction can happen. Wow. We drop the temperature so much that now it's like it's not happening at all. Okay, they are moving really slow. I mean, we can speed them up a little bit. Oh, for the love of... Give me some slope, thank you. Okay, and so now we can see a little bit of slope on that because now we're getting successful reactions. Kind of make sense? Okay. So the idea is that you're playing around with those variables that we've been playing with through all of our calculations, and now we're seeing it manifest both in the particle motion and in our plots. Kind of make sense? Okay. Okay. When did we started at 10? Started at 10? Okay, started at 10. So now what we're going to move to is, come on, why are you not moving? Do what I ask. Okay, a little bit of kind of thought discussion statements. We're looking at a whole bunch of different concepts all coming around in and out real fast. And it can be hard to manipulate and understand what's going on within these things. Okay? It takes time to learn this content. So this is not necessarily, this isn't focused on the content for your exam. Okay? What this is focused on is now what you should be doing. Okay? Realize that learning takes time. Right? So what you're trying to do is spend time over a larger, or spend effort over a larger time period to make connections between the content to allow you to hold that knowledge and allow you to actually make the connections between those systems. Kind of, sort of? Okay. So the more time you spend, the more you can start to consolidate pathways to speed the connections. Because really, if we consider what's happening in lecture, it's more of a kind of diffuse system. We're making these random connections all over the place. You then need to go home and work with the homework, work with the practice exams to say, well, how does that piece of content wrap to another piece of content? So you're trying to bridge that gap. Right? And are you going to bridge it perfectly in the first attempt? More than likely not. And you're going to screw it up, and you're going to create effectively bad paths connecting content within your brain. Right? The more you practice it, the more you can break those bad habits to make a better, faster connection between those pieces of content so that you can do better, faster on exams. But that requires time and effort on your part to really focus your intent behind that studying process. Make sense? Okay. So why do we avoid doing this? Because it's hard. So we will do everything in our power to avoid doing it. Like, oh, I know it's going to suck to read the textbook, so I don't want to read the textbook. Okay? I would rather do dishes. Okay? For me, it's grading. I hate grading. Right? And I hate grading at home all the more worse because the house has never looked cleaner when I'm at home. Because I will do whatever I've got to do to avoid grading, and that means doing the dishes. Oh, I feel like mopping the floor. The floor hasn't been mopped in a while. Let's mop the floor. Oh, I didn't clean up outside. Let's go clean up outside. Okay, those are all important tasks that I need to get done that ultimately I didn't prioritize because they were painful, but they're less painful than me grading. Right? So what we've got to do is kind of fight against that process. I'll admit I'm fully fighting against that process this semester, and I am constantly working through grading and running through things. Right? It is insanely exhausting. Right? But that's the point we're officially all at. You have to spend that time to learn the content and master and move forward with it. Kind of make it? Okay, so different strategies. Okay, I would go back and look at the slides to look at these. Okay, think about how you navigate those processes. Okay, one of the things that contributes, I would argue, to procrastination is a super common statement that all students make, particularly about chemistry. Chemistry is hard, I never understood it. Maybe you never understood it because you didn't spend the time to learn it. Right? And there are people that it just makes those connections and it's easy for. They're like, oh, it's not a big deal. But everybody can make those connections. It just requires more effort to go through and put that in. Okay? That effort can be sidetracked when we go through and procrastinate. Okay? So set aside distractions. Okay? Create scheduled blocks of time where you're going to work on the content. Right? How many of you experienced working on the content and then you couldn't, or you got stuck? And what happened when you got stuck? None of you get stuck studying? Some of you get stuck studying, okay. What do you do when you get stuck studying? Take a break. Yeah, I think I heard it there. You start crying. Okay, it's a miserable experience. Okay, because you don't have a way to resolve that unstick. Right? What's an easy way to fix that unstick? Do your work where there's someone to help you unstick. Okay? A tutor. Okay? You could pay for tutors, or you could go to the tutoring center. I would recommend a tutoring center because technically you've already paid for it. Okay? Leverage the information you've already got to help unstick you through those processes. You could just do your work in the tutoring center and never talk to a tutor because you never got stuck. That's fine. Right? But at least you're putting yourself in a spot where you can actually be more focused and be better and more successful. Make sense? Okay. Last one I think is kind of fun. It is a lifelong practice. Right? We just talked about me. I'm still procrastinating and I'm still screwing things up right and left. Right? It takes effort and it takes constantly going back to and trying to fix. But if we can get you on the right path now and progressing forwards, that can make all your other processes easier. Okay? I have not gotten far enough into the slides, so all the dates are, of course, wrong. I would say procrastination. This is just, I prefer to sleep instead. Arguably, that's even questionable because I'm not sleeping very well. Sorry, TMI. One sentence what this graph is showing. Right? One sentence. We got a plot here. What is this graph showing? Once you think you have your one sentence on what it's showing, that should not have happened. Let's try that again. Why are you doing that? Okay, look at that. Give me one sentence. If you think you got a sentence, draw a graph that shows the concentration of the products over time. This should be pretty simple. Why should this be simple? We just talked about it like 5 minutes ago. This is those making those connections. See what you can come up with. What do you think we're going to get? Yeah, you're just going to keep doing that to me. So we just get out of you. What's going to happen to your concentration of products over time? Your product concentration should decrease.
Increase.
Right? If we're running our chemical reaction, we're going from A, and of course the pen doesn't work very well either. Sometimes I really hate technology. A goes to P. If your concentration of A goes down over time, does that make sense? Should it go down over time? Yeah, as the reaction happens, the concentration of A should start to disappear because that A is no longer present. What happened to that A? It turned into products. And so you should start to see it up here. Right? Eventually, the product is also going to level off. Why should it level off?
It's running out of
there's no more reactant to convert across to those products. Make sense? Okay. And that
would
would,
it always just be the inverse of the graph then?
so should it always be the exact inverse? Does it have to be? What's going to happen to the concentration of A in this case? It's going to go down significantly faster than the product concentration will go up. Why? Because I'm losing 2A for the production of every 1P. So depending on how your reaction runs, it's not going to be a perfect alignment.
It's gonna be, they're ultimately going to be inverse in the sense that one is increasing but slowing down and another is decreasing.
Yep.
Like,
But the
rate of
exact,
change is still roughly the same, it's just a matter of whether or not.
not
like-
necessarily.
Well, that's what I mean, like, if you
Yeah.
have two of a product, then it's gonna
So
be
the
fast.
product should always increase, the reactant should always decrease.
Yeah,
In a perfect one-to-one match, yeah, we would expect them to be perfect inverses of each other. Okay, your rates should be inversely related. Okay, but when you change the way that reaction runs, you're going to start to change how that slope comes out, because there could be scenarios where you're consuming twice as much reactant to produce a single product. That's going to change your slopes of those rates. Kind of, sort of. Okay. Ta-da! Next day. I'm going to hold off on this one. We'll talk about that on, I think, Thursday, because what this topic is looking at is the learning objectives for Unit 1. Why would we want to look at the learning objectives for Unit 1? So what?
We're coming to a closing.
Yeah, we're coming to the close, and in particular, what are we concerned about at the close of our unit? The quiz. So the quiz should be Tuesday, Thursday? Are we Tuesday? We're Tuesday. Your quiz should be next Thursday, to my recollection. So I would argue this Thursday, this is a good thing to be reviewing. Okay, at a minimum, or at the latest, I would argue. So that you can spend the weekend being like, well, dang, I don't know this learning objective. I don't know this one. I don't know this one. Make sense? Okay. So let's look at some other things. A catalyst speeds up a chemical reaction by lowering the activation energy. I don't want this thing up here anymore. So we've got a new plot, and so there's some general pieces of information that change in this, and when we talk about catalysts, they end up changing typically how the reaction runs. Okay, they change the mechanism by which it runs. Okay, so if we looked at a standard reaction, we might go reactant, curve across to product, exothermic are more fun, so why not? Right? And if we added a catalyst, what might happen to our reactions, we're still going to have the same reactants and products, but the catalyst is going to change the mechanism. In this case, our standard format, our mechanism was one step. The catalyst may come in and make it 2 steps. Right? In so doing, what does it do to the activation energy for the reaction? It decreases it. And because the activation energy has decreased, what happens to the rate of the reaction? It increases. Activation energy goes down, rate of your reaction goes up. Okay? Beauty of catalysts is they can be reused multiple times over. Right? They can be metals, small molecules, enzymes. We consider almost everything done in the body, all biological reactions are enzymatic processes. Right? So there is an enzyme that was specifically designed to do that chemical reaction, right? Which is kind of neat. We're built of a billion catalysts running each of those individual chemical steps. That's pretty wicked. Right? If we can find a good catalyst, that can make our synthesis cheaper, it can make it faster, more energy efficient. There's a whole bunch of different things that contribute to that. So a pretty large field is how can we make a catalyst to do a particular chemical reaction? Okay, what does that catalyst need to be able to do? How do we build a system that allows it to work? Right? As you find more catalysts, depending on the value of that catalyst, guess what students get to do? learn about, memorize that catalyst. Yay, okay? That is a relatively low utility or low use, not all that expensive, or not adding that much to our system beneficially. We don't need to talk about that catalyst quite as much. Right? So if we look at biology, you take glucose, and what do we do with glucose? You've taken some biology classes, right? Okay. We have glucose. What do we do with glucose? Turn it into energy. Okay? I could do that right now. I can take a pile of sugar and I can set it on fire. Thus producing energy. Do I want my body to do that?
No.
No, we want it to control how that process goes through and happens. So we've got varying catalysts that come in and allow that chemical reaction to, number one, happen slower, so we don't just combust, right? And control where that energy is going, right? Catalysts navigate each and every single one of the steps of that process. Could they do it from beginning to end? Maybe, but you're now going to look at a massive release of heat. So they break it down into smaller steps, so we get smaller chunks of energy. Smaller chunks of energy mean we don't explode. That's generally a good thing, right? So potential energy, reaction coordinate, that's what we're looking at here. Right, that was our energy diagram. Our reaction coordinate, reactant transitioning to products, and the energy of each of those individual species. What would I call this well? I know the video doesn't get it. Everybody in class, what's that well? Transition isn't a bad word, except we use the transition somewhere else. Where do we use the transition? The transition is usually labeled for the peaks. Those are my transitions. Okay? We could call it a product, because it is a well after the reactant. So it could be a product. Except it's not the product. Okay? I could also call it a reactant, because it's the well before the product. Right? But it's somewhere in the transitioning between those, but I can't use the word transition. That's where we drop in the word intermediate. Could we have multiple intermediates? Yeah, you could have tons of intermediates. Right? But the idea is knowing roughly kind of what the flow of that diagram is. Make sense? Okay. Catalyst speeds up the reaction by lowering the activation energy. Right? So we've seen this plot before, right? We got our fraction of molecules. There's our kinetic energy. This is me trying to make that same plot. Ooh, yeah, there. Right? And we drew another line on this plot, right? We said, what happens when we increase temperature? We kind of squish it and pushes a little bit. So if we increase the temperature, it does something like this. More or less. Probably less. Okay. How do I know which particles make it to product?
Activation energy?
Activation. Well, where's the activation energy?
It's determined by experimentation.
Experimentation. Where is it on my plot? It's not. I haven't put it on the plot yet. The activation energy would be some value that matches the kinetic energy for our particles. So we could go through and say this is our activation energy here. So for this chemical reaction, if we clear that activation energy, we can get product. So for our low temperature, those many particles could make product. For our high temperature, I don't know why I'm changing capitalization, we get that much more particles, right? What does the curve look like if it's got a catalyst? Should I squish it even further? Okay, so
Do you need activation energy to the left?
I'm going to move the activation energy. So I'm looking at a standard temperature. We could pick our low T as our standard. And it changed the mechanism. So the activation energy changes. Instead of doing this big max value here, that looks a little, right? What I'm now doing is saying the catalyst energy is a little bit lower. Why is that powerful? More particles clear that activation barrier. Does that make sense? We now technically have 3 curves on there. Is that confusing? Really? Y'all are fine with that? Okay. That confuses me, but okay, I accept. Okay? More molecules means we increase the odds to go through and produce products. Okay? Which means we increase our rate. Okay, so now we've got an example. Iodide catalyzes the breakdown of hydrogen peroxide, okay, in a reaction known as elephant toothpaste. Okay, I always thought this was a dumb reaction, but I guess that's just my opinion. It is just my opinion. Everybody else thinks it's awesome. We've got our overall reaction. We're looking at hydrogen peroxide turning into water and oxygen. Right? Why does it foam up then? Is water foamy? Is gas foamy? Do you see the foam? Is gas foamy? Why is it foamy? Soap. You add soap to it. Now when the oxygen forms, what does it do? The soap is forming micelles, and the air is bubbling through it, causing bubbles to form. And because your air production is enough, you're forming a whole hell of a lot of bubbles. That's your toothpaste. Right? So, in any case, step 1, we've got our reaction. So iodide can be added to this reaction to speed it up, to make it go faster. Because if I just take hydrogen peroxide, set it on the counter and add soap to it, I'm not seeing anything fancy. But if I add just a little bit of iodide to it, now the production of oxygen increases drastically, bubbles through, causing the soap bubbles to form, and I now get my elephant toothpaste in this big dramatic system. Right?
So does hydrogen peroxide naturally decompose then?
Yes.
And in this specific case, this isn't like the iodine nor hydrogen peroxide. You're adding something else, this being the soap, and the reaction created from the decomposition of the hydrogen peroxide is what causes all the soap to foam up.
Yep.
Because it's a faster reaction.
Yep. So if we go through and look at this, where does the catalyst show up in the mechanism? So if we look at the overall reaction, do you see the catalyst? No. Right? Because it's not supposed to be a reactant or a product. Where could we draw it if we wanted to draw it in our reaction? Okay, I'm not drawing phases, deal with it. If I can't draw it as a reactant and I can't draw it as a product, where can I draw my catalyst?
As an intermediate, like in the arrow?
In the arrow. It's not an intermediate, okay? We're putting it in the gray space between that is neither a reactant nor a product, okay? And so we could call that a catalyst, and we could say I minus in there as our catalyst, okay? Usually what we'd want to do is add the word cat next to it because they're nice and fluffy. It's standing for catalyst, right? So where does the catalyst show up in our mechanism? That's our overall reaction. Where does it show up in the mechanism? What is that? Okay, it shows up in step 1. Where in step 1? In the reactants. Okay? Does it make sense for the catalyst to show up in the reactants? Yes, the whole point is that it has to get in there and cause the chemical reaction to happen faster. So it has to somehow be involved with the reactants. If it's involved with the reactants, what does that start to suggest it is? A reactant. So how do we know it's not a reactant? Where else does the iodide show up? Now you don't want to answer? Okay, that's fine. It also shows up as a product. Okay? So if we look at our overall reaction, this, by the way, we talked through. You can go back and look at the older videos, assuming it recorded then. Our iodide, do I have a pointy thing? I don't have a pointy thing. Right? Our iodide is showing up as a reactant and later as a product. And when that happens, we call that a catalyst. What happens when it shows up as a product, then later as a reactant? That was an intermediate. So you're referencing different pieces along that path. Okay? When do they first show up? Where do they second show up? Kind of make sense? Oh, I actually answered that question. So I'll leave you to write the last part of the question. Write a rate law for this mechanism. Or we'll get your question first.
Well, no, there's probably more than two questions.
Okay, a you question? Then I'll pause that.
I have,
So,
so I was chatting with that one.
okay. Our rate law, let me just finish that out and then I'll come back to you. So what is our rate law for this reaction? First, rate, good, equals K. I've been real sloppy with it. It's going to haunt you later. It should be a lowercase k. Make sure you're aware of that. It's a lowercase k. Because capital K's and lowercase k's look almost identical, so be careful with that. Okay, now times what?
H2O2 squared.
All right.
Bracket.
So we could say H2O2 squared. Is that the rate law for this reaction? No. Okay. That would be assuming the overall reaction was the mechanism. Is that true? No. The information underneath says that's the mechanism. 2 steps. And in those 2 steps, which step do I care about? Why step 1? The slow step is the one I care about. How many times did H2O2 show up in step 1? Once. Because that's a mechanism, now I can bring the coefficient into my order. That's H2O2 to the first power. Is this now the proper rate law? No, because I haven't fully elaborated what step 1 is. What's the other reactant in step 1? Sorry, minus. Now we have the rate law for the overall reaction. Okay, which is really weird. You're like, but I didn't have iodide in the overall rate law. It doesn't matter. I care about the slow step. Our rate law comes from the mechanism or from experimental data. It does not come from an equation. So you have to make sure you've differentiated between those two. Officially, we're done. I know there's at least 2 hands. I'll come to those 2 hands and